Welcome back, and today we're going to consider similar problem comparing two populations means. So we're going to still discuss numerical data, but this time around the data is going to be collected differently. Okay, we will talk about matched pairs. So in the previous lecture we discussed how do you analyze independent samples, but now let's take a look at the matched pairs. Well, first of all, all the previous, the previous problem that we looked at with independent samples we call the data observational. Why? Because we pretty much don't apply any effort to prepare data in any special way, right? Sample number one is random and hopefully representative of what the population looks like. And sample number two also is random. They're completely unrelated, and every time when I take random sample, I'm pretty much picking up random data points from my distribution. Okay, things are organized a little bit differently when we are talking about matched pairs. So matched pairs we're going to call experimental data. The reason for that is, as we discussed in the previous lecture, my sample number one is the only sample that's random, right? I pick sample number one randomly, but sample number two I hand pick. Essentially, I'm saying I will look at what my different data points are and try to find from population number two an observation that matches that specific data point somehow using some criterion, right? That's how we collect the data. So the bottom line here, I guess I'm trying to say, is by looking at the samples themselves, you will never be able to tell if these are independently collected samples or matched pairs. So you have to kind of study carefully, learn carefully how the data were obtained. The process of data collection is what will tell you if these are independently collected data samples or are they matched by some criterion. Okay? So experimental data is more controlled, in other words. When we're trying to collect matched pairs, we're trying to eliminate the effect of certain factors. Like, for example, we discussed that we can collect sales from stores before advertising and after advertising, right? And there are two ways how you can do it. Sample number one can be random set of stores, and sample number two can be random set of stores. What we'll get into the mixture when you collect these two samples is you will get differently sized stores, right? In sample one, you get more high stores. In sample two, you will randomly get more smaller stores. That's not good. Then it can be that demographically stores are very different. One is located in the densely populated area. Another is in not so densely populated area. That will affect the sales. So you're measuring not just the effect of advertising, but also size of the store, average income of the population that lives close to the store, population density, all kinds of things, right? While what you can do is say, well, sample number one is random, and sample number two I'm going to just take the same stores. So therefore, you're looking at the same demographics, same income, same store size, same everything, right? And now you kind of isolated only the effect that you're looking at. And that would be, did the advertising have any, increasing effect on sales or not? Not at all. So therefore, experimental data allows you to answer the question more accurately, so to speak, right? Because you're isolating the effect of undesired factors. Okay, so let's take a look at the problem. MBA starting salaries. Is that true that finance, people who are graduating with MBA in finance are getting offered more money, on average of course, right, than people who are graduating from the MBA program and they have marketing specialization? Okay? That would seem to be the case generally because why? People with finance degree, they go into banking sector, right? Financial companies, investment firms, Wall Street possibly, right? And typically salaries there are high. Okay, so there might be something to that statement. So one way how you can collect it, of course, I mean, to prove or disprove that statement, we have to collect the data and analyze that. That's all there is to it, right? But there are two ways how you can collect the data in general, right? Way number one would be to say, let's take a bunch of MBAs graduating with finance degree and record their initial salary. And then let's take another group, bunch of MBAs graduating with marketing degree and record their salary. That would be independently collected samples, right? But what can happen is the offer, initial salary offer, can actually depend on what your GPA was, right? The higher the GPA, the more money they are inclined to offer you. That may be the case, right? So therefore, if we're just collecting random samples of students from two concentrations, we're kind of allowing the GPA to run wild, right? Whatever happens, happens. So in first group, we may end up with high GPAs, right? And people from marketing, from finance concentration, their GPA randomly can be higher than another group, right? And that may by itself mix into the analysis, right? And we want to isolate this, right? So how about that? We're going to collect first sample, people from finance, MBA, randomly. Whatever their GPAs are, fine. Let it be, okay? But second sample, MBAs from marketing, we're going to hand pick them. Not just any MBA, but MBA that matches, whose GPA is matching GPA from the first group, okay? So marketing people will be hand picked to match, well, not precisely, but closely, the GPA of the people in the first group. So therefore, now we're dealing with matched pairs, right? Now let's take a look at the data. So if you go to Scholar, in jump data sets, you will find a file MBA salaries. So go ahead and download that and open it up. Okay, and there it is. All right, so what I have is 42 observations in sample 1 and in sample 2. But as we discussed, I'm dealing now with matched pairs, right? So specifically, first line, let's take a look at first line. A person from finance, MBA program, got the offer for $68,357. And the person from marketing is $66,135. What's common between these two people? GPA, right? They have matching or very close GPA. Second line represents just another group, right? And look at that. What happens is I still have the same kind of same relation going on, right? Finance person gets slightly more money than the marketing person, 67,119 versus 64,242. And again, what's common between these two people is they have very close GPA. It can be different from line number 1, right? Line number 1, for example, their GPA is around 3.52. And line number 2 could be around 3.72, right? So it's different GPA, but it's common between these two observations. And the same consideration applies to all the other entries, okay? That's what makes these observations to be matched. So if I didn't know this story, basically, let's go back. If I didn't know this story, how the data was collected, somebody gives me this data set and tells me, okay, analyze that. Well, how the data is collected? What are these numbers, right? Salaries. Okay, how did you collect them? Was it just random sample 1 and random sample 2? If that's the case, then that's independent analysis, right? But it's not the case. So I have to know that these are matched by certain criterion, by the GPA, okay? So it's not, by looking at the data, you will not know if it's independently collected or matched pairs. You have to know the data collection process, how the samples were obtained. That will tell you what are you dealing with, okay? Which case, independent or matched. Okay, now let's take a look at how exactly the test is done. Let's see. Let's actually talk about required condition. Every time when you're testing hypotheses in statistics, there is a certain condition that you have to satisfy, right? In our previous analysis, when we talked about independent samples, what did we say? That you can use t-test for independently collected data if sample number 1 is normal and if sample number 2 is normal, right? Separately. Let me tell you how the matched pairs t-test is done. Okay. First thing that the software calculates behind the scenes is the matched pairs differences. So what does that mean? That means that if I'm looking at the first line, for example, okay, 68,357 versus 66,132. So first thing that the software will create is difference between finance number and the marketing number on the same line between the matched observations. And then it will do the same difference, calculate same difference for the line 2, line 3, etc. for all the lines. So instead of column 1 and column 2, two different columns of data, we're going to calculate one column of paired differences. And after that, software will treat that column as if this is what we're analyzing. So it's going to essentially analyze one column of data using the t-test. Okay? So it's not analysis of column 1 or column 2. It's the calculate the matched pairs differences and then work with just one column of data. That's how the test is done on the back end. Okay? So the requirement for matched pairs t-test is actually different from independent samples. When we had independent samples, we had to test sample 1 for normality and sample 2 for normality. And both of them had to be normal. In matched pairs t-test, we have to just make sure that sample 1 minus sample 2 is normal. The column of paired differences is normal. So sample 1 can be completely non-normal, and sample 2 can be completely weird and non-normal. But as long as the differences between the matching observations are normally distributed, we are fine. We can use the t-test. Well, in fact, let's go ahead and actually take a look at how our columns are distributed. Okay, so I'm going to click. Oh, just look at the distribution, right? Distribution, finance and marketing, just in formula. Okay, what do you think? Do they look normal? They're fairly normal, right? This observation looks very normal, and this observation looks also very normal. So I don't have a problem even on the individual, distributions level, right? But here is the downside, though. Okay, it looks like JUMP does not provide us a tool how we can compute the how can we test the distribution of differences. Okay, so in other words, we have to actually do one more extra step before we do anything else, and that extra step would be to calculate the differences. All right, so let's do that. Go ahead and double click on the column number 3, the empty column. Okay. All right. So this is where the differences are going to be located. Now let's rename our column number 3. Let's double click on that. And column 3, I'm going to rename differences. Differences. Okay. And you know how you can nicely calculate differences in Excel? You just start typing in the cell, right? JUMP does not provide that capability, so we have to actually create a formula for each column. So I cannot edit formula on the cell level, right? In Excel, you can do it. You can type formula 1 in cell 1, and in the next cell, it's going to be different formula. Excel doesn't care, really, right? JUMP actually does not allow you to do that, so you have to define the formula for the entire column. So we don't do it on the cell-by-cell basis. You have to create a formula behind the entire column. How do I do that? Well, I go to column properties, right there. Okay, there is a button, column properties, and the very first thing on the list is formula. So I go ahead and do the formula, and it adds to the list of properties that, this column, is going to have a formula behind it, right? But I need to create a formula. So let's go ahead and click on the button Edit. So right now there is no formula, right? It just says that there's going to be a formula. So now let's create the formula, edit formula, and it creates opens up the editor. Okay? So really what I want to do is subtract finance from marketing. Right? Column 1 minus column 2 matching observations. So I click on the finance, and in this area you can see the formula shaping up. Right? I click finance, and I click minus sign, and then I click marketing, and there it is, finance minus marketing. Okay? And then I just have to say okay, okay, and there it is. So you can see that some of the differences are negative, right? Most of them are positive, actually. Some are negative. So I think it might be true that finance guys, they do earn more money on average than marketing guys, right? Because most of my differences are positive. So finance is higher, right? Okay, but first things first. Why did we create the differences? To test normality, right? Remember, the only requirement is paired matching differences have to be normally distributed. Well, let's test the normality of my newly created column. How do I do that? Well, same mechanism as before, right? I have to create a distribution. Let's do the distribution of differences, right? I don't care really about sample 1, sample 2 individually. Maybe it's normal, maybe not. Don't know, don't care. As long as differences are normal, that's the only thing that's important. Okay? So here is the distribution of differences. Looks kind of bimodal a little bit, right? So I'm going to look at more graphs. So one of them is normal, where is that? Normal quantile plot. Supposed to be aligned along the diagonal, and it is, right? It is aligned along the diagonal line, which is good. So now let's do the Shapiro-Wilks test, right? So I go to the differences and say continuous feed normal, and it just feeds the normal curve into my histogram. And after that I have to run the Shapiro-Wilks test. In the fitted normal, I say goodness of fit. We did that before, right? Several times, so we probably used to that already. So what am I looking for? High p-values or low p-values? For high, right? For the data to be normal, it's got to have a high p-value, right? And it is 0.726. And right there at the bottom it says normal data comes from normal distribution. So statistically, my differences between matching observations are normally distributed. Which means, by the way, let's actually do that. Let me be formal, right, about this thing. So let's go back to the lecture notes and open up analysis flowchart, right? This one. I'm actually going to just open it from here. Analysis flowchart right there. Okay, so if I want to be formal and see which test actually I have to use, I need to start from this node of the decision tree, right? I'm comparing two populations. MBAs graduating with marketing degree versus MBAs graduating with finance degree, right? Data type, interval. The next one is, we discussed it, right? What are you testing? Are you testing variability or center? We're testing center, right? In this course, we're not looking at variability, right? So this part, we're never going to touch, okay? At least in this class. So we're looking at centers, means preferably. All right, experimental design. Are the samples independently collected or are they matched pairs? Well, these are matched pairs. We discussed that, right? And the last question is how differences between the matching observations distributed. If they are normally distributed, then I have t-test for the difference mu1 minus mu2. If they're non-normal, differences are non-normal, then I have to use something else, which is a non-parametric test. Wilcoxon signed rank sum test. Well, we just tested the differences for normality, right? Turned out to be normal. So therefore, I can go ahead and proceed with my t-test. Okay? So all these ideas about the mean and mu1 minus mu2, they are all valid. Okay? So now let's take a look at what exactly am I testing, right? I don't need to look at the p-values because writing down the hypothesis is just a matter of addressing the question posed in the problem. So let's go back to the problem and let's see what was the original question. Is there a difference between starting salaries for MBAs from finance and marketing? More precisely, is that true that finance majors are offered higher salaries than marketing majors? And that becomes my null or alternative. What I'm trying to investigate. Is that a null or is it an alternative? Alternative, right? So therefore, let me go ahead and write down, that's from yesterday, right? Let me go ahead and write down the hypothesis, okay? So what I'm investigating, that is my alternative, is that the average salary for the finance concentration is greater than the average salary from marketing concentration. That is what I'm investigating. But remember, everything that we test in terms of two populations should be in the form mu1 minus mu2 or p1 minus p2, right? So therefore, I have to rewrite this hypothesis. In what way? Well, one number is greater than a number, another number is the same thing as first number minus the second is positive, right? Or you can subtract marketing from both left side and right side. So on the right side you will have 0, and on the left side you will have the difference. Finance minus marketing, MKTG, and that is greater than 0. So if I find in favor of my alternative, and I'd say yes, yes, it's true that marketing guys are making more money, being offered higher salaries in general on average, right? Than finance guys offered more money on average than marketing guys, right? So my null hypothesis becomes that a finance, opposite of alternative, right, minus marketing is less than or equal to 0. This is what I'm testing. Okay? All right. So now let's go ahead and test it. There's not much to do other than go ahead and test it. Now, testing of this hypothesis is kind of, we're going to use slightly different menu than what we used so far, okay? If you go to the menu Analyze, and over there, Specialized Modeling, you will see an option that says Matched Pairs. Okay? Analyze, Specialized Modeling, Matched Pairs. Okay, and here in the Matched Pairs, I need basically to move my columns that I'm trying to compare in this area, paired responses. You can see there it says required numerical continuous variable and required another numerical continuous variable, right? Now, it's important actually to keep an order of things. Here's how we formulated our hypothesis, right? In terms of finance minus marketing, right? That's how we formulated them. I should keep the same order probably, right? And this part, let's see, let's kind of experiment. What happens if I drag the finance into this area first and marketing into this area next? What will it test? So when I click OK, it shows me some plot. And what is it testing? It's testing difference between marketing minus finance, right? That's what it's showing. So on the top it says marketing minus finance, while in actuality I want to test finance minus marketing, right? So it looks like when you're setting this thing up, you have to drag your second column first, right? In the first place, yeah. So let's do it again, right? I mean, that's a little weird, right? You would think whatever you drag first is your A minus B, whatever you drag next, right? But apparently jump doesn't work that way. So specialized modeling, I'll do it again. Matched pairs. And now I'm going to drag marketing first and finance, and hopefully as the result it'll test the difference, finance minus marketing for me, right? So I click OK, and there it is, testing difference between finance minus marketing, okay? So over here, what it shows actually for me, you see the 3 red lines. Let me go ahead and make it bigger. three red lines. These three red lines, it's very easy to interpret. Okay, so first of all, it says, let's take a look at this summary, right? This table that I have over here. Basically, it says that finance people are offered, on average, $66,387. That's what it computes. We saw that before, right? Marketing people are offered, on average, $63,278. So it looks like, on average, finance people are paid more than marketing people, but of course, what I'm dealing here is not the population numbers, these are sample averages, right? And sample averages, as we know, can be deceiving, right? How confident we are that these are actual population averages? 0, right? This is just a sample, and small one actually. It's not a huge sample, okay? And then the next thing, as you can see, it reports what is the difference between the mean finance minus mean marketing. So it looks like it should be over $3,000, right? In fact, it's over $3,100. And that's, it computes the average right there. $3,108.48. That's the difference between these two samples, okay? So this solid red line on the chart, it's actually your average difference. Reported right here, $3,108. Can you guess what the dotted red lines above and below represent? If you would have to guess. That would be a confidence interval. 95% confidence interval for what? Mu1 or mu2 or mu1 minus mu2? Mu1 minus mu2, right? So, therefore, we can not only test hypothesis, but we also can estimate the confidence interval for mu1 minus mu2. All right? But let's go ahead and test the hypothesis first. Okay? And let me go back to my formulation of hypothesis right here. My alternative that I am testing, but the difference, finance minus marketing, is greater than 0. That's the form that I'm testing. So therefore, I'm looking in right tail, left tail, or both right and left. Which tail I'm testing? If it's greater than 0. When it's greater than, you're testing the right tail of the distribution. When it's less than, you're testing left tail of the distribution. When it's equal, not equal, you're testing both right and left. So specifically here in this problem, I'm testing right tail of the distribution, right? So here is the probability. I should look for probability greater than the t ratio. Here is the t ratio computed for me, okay? And there's a complicated formula behind the scenes, which we're not going to discuss. It's fairly involved, okay? So I'm looking in the right tail of the distribution, so that should be probability greater than the t-score, right? And probability is very small, less than 1%, okay? So what do? Coming back to my formulation, my p-value for this test is, I don't even know it numerically, all I know is less than 0.0001, right? So what do I do with this p-value? Keep the null or reject the null? Reject, right? Small p-value, you reject the null in favor of alternative. Okay, that's ugly. In favor of alternative. And what conclusion do I make from that? Do I have a statistical proof sufficient enough to claim that finance graduates are offered averagely more money than marketing people? I found in favor of alternative, right? And alternative says that, yes, average salaries in finance concentration are higher than in marketing concentration. So this difference that we found, $3,108 between sample 1 and sample 2, is actually statistically significant difference, right? For us to say that, yes, it's not just a random fluke by the, selection of samples. It's the statistical confirmation that you cannot observe the difference purely by chance, purely by accident. The likelihood to observe that if the salaries are still the same and you just randomly observe that difference is very small, much less than the 1%. Okay, so therefore, It's not that we observed a very rare event, it's the confirmation that our null hypothesis that salaries are the same is not true. So finance people do get paid more on average. Okay. Now here what I wanted to do also is to illustrate what would happen if I would use incorrect analysis. So we discussed that this was a classical matched pairs problem, right? You take MBA salary and you match another MBA so that it has similar or very close GPA value, right? So that's clearly a matching matched pairs, right? What if, suppose that I'm in the exam settings or maybe working, right? And boss tells me to, I'm working at the career service office, okay, at the university. And director of the career services tells me, hey, you know what? We are graduating MBAs. I want to be able to tell parents, something about, salary statistics. Can you take a look at salary distributions and tell me that, finance people, we want to promote our finance program. So let's see, maybe finance MBAs get more money. Can you do that for me? So I collect the data. I know that the data was collected, matching MBAs, but, something doesn't click. And I think, well, independent samples. So let's take a look at what would happen if I would perform incorrect, wrong analysis. Treat these samples as independently collected, right? So I'm going to delete the column of differences because samples are independent. I don't compute any matched pairs differences, right? Okay. So suppose I did all of this, and I believe we looked at the distribution, right? Distributions look normal. Sample 1 normal, sample 2 normal. So I'm good to go, right? I can use independent samples t-test. So what I'm about to do is wrong, actually, right? But let's see if my analysis will give me a different answer if I'm using a wrong type of analysis, okay? Remember how we performed the independent samples analysis? What do we do? You did that in the homework today, right? We need to, first thing, what do we do with columns? Stack them, right? For independent samples, we need to stack the columns. So I'm going to go to the tables, stack, and there it says, which columns do you want to stack, my dear friend? And that would be finance, stacked with marketing. And then it says, well, we're going to create 2 new columns for you. One will contain the data, the measurements, and another will contain labels, right? How do you want to call them? Well, they offer data and label, which makes sense, right? So how about I'm going to call data, my measurement is salaries, and the column with labels, I'm going to call major, right? Major, MBA major, finance major, or marketing major. Okay? So therefore, I'm going to study the effect of MBA major on the salary, right? So factor of study is going to be a major. The response variable, the measurement variable, is going to be the salary. Does the salary change when you're changing the major, right? That's going to be the purpose of the study. All right. So I click OK, and it creates a new data table for me. So it just basically stacks them, takes one line at a time, right, and picks one from column 1, another from column 2, and it goes line by line. All right. Fit y by x, that's what we used, right, in the previous class. So here is the shortcut, or you can go to analyze, fit y by x, same thing. So let's use the shortcut. All right, and then it says, well, you're studying the effect of a factor, which is a categorical variable, right? Major is a categorical variable. Finance or marketing, it's not a number, right? You're studying the effect of the factor on the response, which is a salary. So salaries goes into responses, and MBA major goes into the factors. Okay? And then I get the window with output, analysis output. All right, this is just a scatter plot, right? It's not very informative. Well, if I'm looking at this picture, what does that tell me? What's the only probably piece of information that I can see from that. That salaries of marketing people are more distributed, more variable, right? So there may be a slight difference in the standard deviation, right, between my two majors. But I can't really see much other than that. So let's ask for the summary. I'm going to ask for mean and the standard deviation summary. So means are the same, right? We looked at them before. Finance people 66,381 on average. Marketing people 63,278 on average. Now, remember we discussed that there are two different ways how to perform the independent samples analysis. We can assume equal variances or we can assume unequal variances, right? So that's a judgment call essentially, right? You can take a look at standard deviations and say, hey, this standard deviation looks close to this one, or are they horribly different? What do you think? 13,948, so 14,000, right? Versus 16,849. Are they fairly close, or are they horrifyingly different? It's a judgment call, right? So I'd say fairly close, right? The difference between them is what? It's about $3,000, right? So about 20% difference, okay? So it's not a huge difference. So let's use the assumption that the variability of both samples is the same, or at least very close, okay? So therefore, what I need to do is to go into the red triangle menu and call up this item, right? Which says means Anova pooled t-test. And you can see that actually it says it right there, okay? Assumes equal variances. All right. So I'm testing the same hypothesis, by the way, right? I'm still answering the same question that I imposed before. Is that true that finance people on average are getting paid more than marketing people, right? Hypothesis didn't change. I'm using a different tool to answer this question, but what I'm testing really has nothing to do with the tool selection, right? I'm trying to answer the same business question. Finance salaries on average are higher than marketing salaries. All right, so therefore I'm still looking in the right tail of the distribution. So which means that which probability do I have to pick? Greater than absolute value of t, greater than t, or less than t? In the right tail, greater than t, right? So what do we have? Let's see. Oh, and I'm testing here. Yeah, that's that sucks, right? Because it flipped on us, right? Yeah, it flipped on us. So now it's looking at the difference, marketing minus finance. I'm looking at these p-values, I'm like, wow, it got to be this number, 0.1799, but it's actually testing the left tail of the distribution. The reason is because it flipped. Now it's testing not marketing minus finance, not finance minus marketing, but the other one, right? Well, it's easy to fix actually. If we go back to our hypothesis, this one, right? If I want to change my H1, make it appear different, okay? So right now it's testing finance minus marketing. What will happen if I want to test marketing minus finance? I have to multiply both sides by -1, right? And when you multiply both sides of inequality by -1, what happens with the sign? It flips, right? So therefore, this alternative hypothesis is really equivalent to multiply left side by -1 and multiply the right side by -1, okay? -1, wow. Okay, what did I do? Pen, this one, right? Yep, by -1. Okay, and on the left side you will have mu marketing, MKTG, minus mu finance, FINC. The sign flips around, so therefore it becomes less than, and 0 is still 0, right? So these two are just different forms to write the same statement. Agree? So the reason why I did that is to match what the jump does for me. It's testing marketing minus finance. So therefore, I have to understand how to write the hypothesis in terms of marketing minus finance. And That's the way it is. Okay. So now I'm testing which tail of the distribution? Left tail of the distribution, because it's less than, right? Okay. So with left tail of the distribution being tested, I'm looking for probability less than a t-score, right? T-ratio. And that would be 0.1799. Okay. So therefore, my p-value 0.17. What was that? 99?
No.
99. Okay. 99. How does that compare to any really value of significance alpha that we can choose? We can choose 1% or 5% or 10%. P-value is greater, right? So it is greater than alpha. And what happens when we're dealing with greater than alpha p-value? I fail to reject the null, right? So null now stays, and alternative, I don't pick it. Do you see how things changed? Before that, when we treated the samples as matched pairs, we rejected the null, and we said that yes, finance guys are getting paid more on average than marketing guys. But if we use incorrect analysis, our answer flipped. It's not universal, of course. It's just problem specific, right? In some problems, you will find that it doesn't flip, okay? You use the matched pairs or independent samples, same thing, right? You reject the null or you don't reject null, same thing, okay? But in this specific problem, I have to tell you honestly, right, that I doctored these numbers, okay, in such a way that if you use the matched pairs, then you will get one answer. But if you use incorrect independent samples analysis, the answer will flip around. Okay, so it is possible. It's not universal truth, but it is possible. So the moral of the story is you have to make sure that you're using the right analysis. Okay, and moreover, that's what I do on my exams. Okay, I leave you clues how the data was collected. Is it some independent samples or matched pairs, but I prepare my data in such a way that if you misjudge it, okay, and use the wrong analysis, your answer will be flipped, okay? And that's how I know that you use the wrong analysis when I'm grading. If I see the incorrect answer that relates to a different alternative analysis, and I know that you picked the wrong tool, okay? I probably shouldn't say that because I'm kind of letting you in the secret, right? But that's me. Okay. Make sense? Any questions, ladies and gentlemen? Shannon?
All right, I ran the test on that the variances are equal, and it says that they are not.
Oh, they're not equal. Yeah.
Well, I'm just playing with the jump.
Yeah, no, I understand. Yep.
So I did the one-way analysis, unequal variances.
Okay, yeah, I was actually about to do that. So all of these things, we did them assuming equal variances, right?
Right, so I was just questioning.
Yeah, what happens if variances are, what happens if we misjudged it, right? So let's actually do the same thing and see if the answer changes at all. So now what I'm going to do is perform the t-test that assumes unequal variances, right? So it's a slightly different formula, and there it is, okay? So it's still marketing minus finance, right? Assuming unequal variances, all right? And I'm looking at same hypothesis, right? Marketing minus finance less than 0. That's what I'm testing. So I'm looking in the left tail of the distribution. Look at that, probability less than t, 0.1799. So it's the same p-value, right? And we'll get the same conclusion, right? Now again, this is just for this problem. In general, if your data is different, your results for the same variance versus not the same variance, unequal variances, will actually differ. In this case, I guess we were lucky, right? No matter which formula you use for equal variances or for unequal variances, it gives you the same p-value and therefore the same conclusion, okay? All right, and we have actually enough time for one more example, which I rather like, this example. So let's go back. And these slides basically, I'm not going through the slides because Essentially, the slides contain all the steps that we did. First, create differences, create formula, then test differences for normality, then record the hypothesis, and then go to the analysis, special modeling, matched pairs. So all the steps are outlined. Okay, let's address this question. Right, kind of practical one. The waiters and waitresses are the same types or different types. Talking about the equal compensation in the workplace, right? Well, tips is not exactly compensation, right? Tips is pretty much what people leave behind. What's the general adopted practice in the United States? The amount of tip. Standard thing. 20%? 20%? Okay. I heard 15, 20, yeah. But it could be that people leave behind different amount of tips for men and women, right? If you would have to guess, who would earn more money in terms of tips? Males or females? Males or females? If you would have to purely take a guess. Females, right? Because they are more attractive than males, right? And therefore people like to be nice to them, right? So it yeah, and yeah, because males are more likely to be more paid, so therefore people are like, okay, I know that you're getting more money, so I'm going to leave you less tip, right? Could be that. All right, but in this study, we're going to actually address a different question, right? Are they earn the same tips or different tips? So we're not going to say males earn less or males earn more. That's what we're going to study. We're just going to study, is there a difference between them or is there not a difference between them? They earn the same amount, okay? So at 1% level, make a conclusion. But let's read first how the data was collected, right? To answer this question, a restaurant consultant did a study. The study involved him going to random restaurants, right? And in these restaurants, he records the percentage of total bill that was left behind as a tip for one randomly selected waiter and one randomly selected waitress. And he picked 50 restaurants. So in each one, he picks male, female, and records the percentage, right? The tip percentage. Then he goes to another restaurant, picks male, female, records the tip percentage, right? So that's how the data was collected. And let me close all the unnecessary windows here. And let's open up the data set. Supposed to be in jump data sets, close to the bottom. Okay? So waiter versus waitress. That's what we're analyzing. Let's open it up. And there it is. Okay, so I have a bunch of tips for males and females. So in the first restaurant, right, the tip was 11% for the waiter and 11% for the waitress. Same thing. Second restaurant, 12 and 12. In the next one, the waiter got 15% and waitress got 18%. Then we have 11 and 5. Waitress again gets more, right? But in restaurant number 5, we have 10 and 8. Okay? So the data is not so, like, it's all over the place, right? Sometimes males get more, sometimes females get more. All right. Well, ladies and gentlemen, let's be formal about that, right? So I'm trying to kind of start you thinking in terms of statistics is a toolbox, right? Which tool do I pick? All right. So in this specific question, do I describe a single population or compare two populations? Or do I compare three or more? Or do I analyze relationship? Which one do you think I should pick? Should be my starting point. I'm comparing males versus females, right? So it's got to be compare two populations. What data type do I have? Interval, ordinal, or nominal? Interval, right? Right there. And of course, I'm discussing central location, right? Because we don't pay attention to variability. Now, here's the important question. Do I have independently collected samples for males and females, or are they matched by some criterion? What do you think? Independent or matched? So the explanation should be in how the data were collected, right? the process of how did we obtain these numbers. How did we obtain that? We went to 50 restaurants, and in each place we get one male server and one female server, right? And we record the bill percentage. Okay? So, what do you think? In other words, is there anything, like if I click on first line, right? 11 and 11%. Is there anything that unites these two observations? It's common between these two observations. Between that waiter and that waitress. What do you think? What might that be? Something in common between them.
Same customer.
Well,
The same, like, available price.
not necessarily, right? One bill can be for $20, another bill can be for $50. It's just the tip was 11 and 11%, right? So bills can be different. It's the same restaurant, right? True or false? What can happen is if I go to the different restaurants, let's use the word classy place, right? As compared to not so classy place. Okay, so if the restaurant is really expensive and upscale, people who go there, they probably have enough money, right? So they tend to be more generous, right, on their tips as well. So therefore, percentage can be higher, right? And in not so classy restaurants, just regular, lunch place, tips can be lower in general. So therefore, we want to exclude that factor, right? So in order to see how males and females are doing, regardless of, is it upscale restaurant or is it not so upscale, it got to be the same place. Now you're comparing apples and apples, right? Same restaurant, how are males versus females doing? Okay, so the factor that matches these two observations is the fact that these two numbers are coming from the same restaurant, from the same place. Okay? Make sense?
How would you
Christian?
know that? Or how do you even infer that?
Oh, it's in the description.
It
Right?
is in the description.
Yeah. To answer this question, a restaurant consultant went into the study involved recording the percentage of total bill left as a tip for the randomly selected waiter and one randomly selected waitress in each of the 50 restaurants. Right? So in other words, this column is collected in 50 restaurants, different, and this column is collected in the same 50 restaurants, right? So we go to a place, get one male, one female, and record their percentage, right? These are not 50 restaurants and 50 other restaurants, right? It's the same. It's pretty much same deal as we discussed about the, marketing, right? You can get one set of stores and completely different set of stores, or you can say, hey, let's take a look at the same store before the advertising and after advertising. That's what makes them click, same store. Here, it's the same place, same restaurant, right? So we're dealing with, let's go back to our decision tool, right? We're dealing with matched pairs. So the next important question is, well, it can be t-test, or it can be Wilcoxon non-parametric test. It all depends on how differences are distributed. So just like we did before, let's compute third column of differences, right? So this is extra step that we unfortunately have to perform on the data. Okay, so I compute the column of differences, and there should be a formula behind that. Okay, so I pick a formula, and then I edit the formula. I'm going to say waiter minus the waitress. Okay, and it computes the numbers for me. And as you can see, some numbers are zeros. I don't have a lot of them. Some numbers are negative. Few of them are positive. So it's not a clear cut, right? What's going on? All right. Now let's actually test the differences for normality, because that's an important question, right? All right. So I'm going to look at the distribution of differences, and this is how they look. What do you think? Normal? More or less? Yep. So there is some weird emptiness right here, but that probably doesn't change the picture a whole lot, right? Now let's take a look at the quantile plot. Quantile plot almost perfectly aligned along the diagonal, right? So do you want to run Shapiro Wilks test as well, or is it evidence enough? Yeah, that's good, right? So let's assume that we're good to go. All right, so now I'm going to do the testing, but before the testing, I need to know what is that I'm testing, right? So let's go back to the slide and see what are we testing. Do waiters and waitresses earn same tips or different? Okay, so it sounds like what I need to test is equal versus not equal, right? Equal to 0 would be the same. Not equal would be different, right? So in other words, my alternative would be that average tip for the waiter is not the same as the average tip for the waitress, right? Can be less, can be more, but it's not the same. Okay? And that translates into what? Difference between the waiter and the waitress minus the average tip for the waitress is not equal to 0. So, oh, that's alternative, right? I wrote that as a null. That's alternative. And my null, therefore, is going to be that the average waiter tip minus the average waitress tip is equal to 0. If it's equal to 0, what do I say? They are the same, right? Tips are the same. That's what I'm testing. Okay? And it's got to be t-test because differences are normally distributed, right? Make sense? So now, let me go ahead and do the analysis. Simple as that. So I go back here, and I go ahead and analyze specialized models, matched pairs. So it's kind of different menu, tucked away in some deep menu item, right? So here I don't really care which comes first and which comes second, right? Because I'm really testing equal versus not equal. So it's not the right tail, it's not the left tail, it's both right and left. So it doesn't matter which one you pick first, which one you pick second, right? So it's going to be both tails anyway. Waiter versus waitress, okay, very good. And then I click OK, and let's see. Here is the p-value that I need, right? Probability greater than absolute value of t, because it's not the right tail greater than, it's not the left tail less than, it's both tails, right, of the distribution. So my p-value is 0.0005. All right. Point p-value 0.0005. What can we say about this p-value? It's smaller than any level of significance that we can possibly pick realistically, right? So the smallest that we are used to is 0.01. 0.05 is normal. 0.1 is kind of not so rigorous significance level, right? But it's smaller than our smallest one that we can pick. So p-value is small. We reject the null in favor of alternative. What does the alternative say? The alternative says, nope, they're not the same, right? So waiters and waitresses, they do earn different tips. So there is such thing as waitresses probably earn more, right? How can we actually see that? Let's do something else, okay? You can see, I'm going back to my analysis, right? You can see that there is a confidence interval that was constructed, right? It says upper confidence limit for 95% and lower confidence limit for 95%, okay? But what's that confidence interval for? Is that for the average tip for the waiter or average tip for the waitress? It's actually the waiter minus the waiter, exactly right, okay? So it analyzes waitress minus the waiter, right? That's what it says. The analysis, all this analysis is done for the difference waitress minus the waiter. So therefore, I can write down this. Okay, let me create a new page. I can write down that what we're estimating, and confidence interval is an estimation, right? That's what it is. So it's the estimator of the average tip for the waitress minus the average tip for the waiter. Okay? And it is between lower confidence limit and upper confidence limit, right? And what are they? My lower confidence limit is 0.53, my upper is 1.7, let's call it 9, right? So 1.79 and 0.53. That's what my confidence interval tells me, right? Now what's the interpretation of the confidence interval? Confidence interval is kind of a range of values which contains, with the confidence of 95 in that case percent, our true difference, right? So essentially what I'm saying is I don't know what the actual difference is, and I never will, right? It will require me to find out all tips for all waiters everywhere, and same for the waitresses. Task close to impossible, right? So I don't know what that difference really is, okay? But I'm 95% sure that it's between 0.53 and 1.79. So what do you notice about both lower and upper confidence limit? They're both positive, right? That means that the whole thing in between is also positive, right? It's between a positive number and another positive number. So we can say that mean waiter, or waitress, right? Waitress minus the mean waiter is positive. And we're 99% sure that this is the case. 95, right? 95% sure that this is the case. Which translates into the statement that the average salary for the waiter is actually higher than the average, not salary, tip, right, for the waitress. No, other way around. Wait, here I have waitress, and here I have waiter. Okay? So from analysis of the confidence interval, I was able not just to conclude that they are earning not the same but different tips, right? But more precisely, I was able to state that waitresses actually are getting more tips on average than waiters. So even more information, right? It's not just they're not the same. More specifically, waitresses are getting more money in terms of tips. Make sense? Now that's kind of an illustration how we can use hypothesis testing and confidence interval simultaneously, right? So they can lead to similar conclusions, right? So therefore, these two tools, estimation using the confidence interval and testing of hypothesis, they can be actually used interchangeably, right? You can get the same conclusion using a different tool. Okay? All right, so since we had an exam today, I'm going to assign you only one homework problem, and it's posted already. Okay, so tomorrow, what we'll do first is go over the homework, and we'll go over the exam, and we will keep discussing. The only thing remaining in comparing two populations is we need to discuss proportions. What if your populations are not numbers? Everything that we discussed so far regarding two populations was numerical data, right? But what if it's not numerical data? What if it's a bunch of categories, right? So we're going to take a look at the example of how do you compare proportions. And then after that we will start moving closer and closer towards the multi-population analysis. That would be Anova, analysis of variances. Okay? So that's it for today, and I'll see you tomorrow.